Let's get things started here. So you guys have some questions? Everybody just take a deep breath. I'm going to go one at a time. Braden.
Can you go over 50?
50? 15. Sure.
All the odds.
Okay. All right. So when I look at 15, what do I first need to do to take the derivative of x e to the negative kx? What's the first derivative rule that needs to come into play? Product rule is correct.
How do you know?
Because you have...
Yeah, but... Alright.
Wait, do you mean like why don't we throw a shot?
Yeah. Like how is
Right? So what we should notice is we have some f of x times some g of x. So if we do that, we have f times the derivative of g, and I'm just going to write it this way for a moment until we actually do it, plus g times the derivative of x. Okay, so I'm just going to go slow, trying to show some steps. Now, to do the derivative of e to the negative kx, that requires a chain rule, because I noticed that in the exponent is more than just x, right? So to apply the chain rule, the derivative of the outside is e to the x, right? Yeah. So the derivative of the outside, and then the inside just stays in there, stays the same. And then it's times the derivative of the insides. We'll do that in a second. The derivative of x is just 1, so that's easy. What's the derivative of negative kx? Negative k is correct. And at this point, the differentiation is done. Everything remaining would just be simplification. So if you're doing your homework, you could stop at this point. If it's a free response question on a test, you could stop at this point. If it's a free response question on the AP exam, you could stop at this point. If it's a multiple choice question, there's no way in heck that's what we have written down there is going to be one of the answers for A, B, C, and D. So we should practice doing some simplification just to help us being able to recognize what's, what are a different, a simpler representation for this that may be closer to what might be on a multiple choice. So if I look at this, I would notice that, hey, I have two terms, each of which contains an e to the negative kx. So if I factor that off, I'm going to have a negative kx plus 1 times an e to the negative kx. That's probably where I would stop. Again, if you wanted to make write that as negative or 1 minus kx over e to the kx and move that negative exponent to a denominator, that would be okay. But since the problem started with a negative exponent, I think your final answer can have a negative exponent in it. That's typically the convention that seems to be when I've looked through AP multiple choice questions. If they have a negative exponent or a fractional exponent in their start, they'll have it in the answers on the at the end. Okay, Elena? Yeah. So I just took out the greatest common factor, right, between the two terms. So what's left over here is a negative k times x. So that's this part. And then there's a coefficient of 1 here that we don't write, but I know is there. So that's all that's left. So that's the one that's there. Does that feel okay? Pierce.
What is that written in like the third step? GDX.
Negative kx.
So when you're taking the derivative of something, like e to the power of something, you're going to multiply it by that.
That's the chain rule that happened there. So it just, the derivative of the outside was this piece, and the derivative of the inside is that piece, the inside being the exponent. Does that feel okay? Okay. Isabel.
Does the order in which you write like the answer matter? Like, did I just say like negative kx
No, that's fine. Yeah, it's, again, like you'd recognize the difference
Yeah.
on a multiple choice. It's like, oh, two things multiplied together. Oh, I wrote them in the other order. Oh, like clearly you're not gonna be like confused by that. That's something that's trivial for you, right? So again, like, am I ever gonna require that you simplify something? No. So what I will do is I'll give you multiple choice questions though, where the answers, the A, B, C, and D, are going to be simplified forms or like common mistakes or whatever. Like that's how I will like test that skill the same way the AP is going to test that skill. But if you're planning on many college math classes, you may want the practice on simplifying things because maybe much less accepting of unsimplified answers than I am. So again, like especially in the homework, there's no penalty for getting the things wrong. Like know that you got the calculus right, and then if you goof the algebra at the end, simplifying, like just take that as a learning experience and try to figure out where the mistake is and what the misconception was, and we'll do better as we go. Doesn't have to all be perfect now, but I'm never going to require you to like simplified answer. If you can't get all I simplify it down to, you're wrong, you know? Can you grab the door?
Also, like the two things that you circled, so the derivative of negative kx is the outside, you said, is exponent or
Inside.
inside?
Yeah. Thanks, Talika.
Is this
Okay, go ahead.
third steps the product rule still, or is that? Oh no, that's the.
So the
chain.
product rule was done here,
I don't use the-
and then this is the chain rule, and then everything after is just simplifying. At that point, the derivatives were done. Okay. Rita, you had a hand?
Oh, actually, I can do that.
Okay.
Yeah.
Elena.
Can we do 75?
Okay, jumping right around here. Sure. Brayden, you're happy though with what we did there?
Yeah.
Okay.
That's amazing.
Yeah, I know. Yeah.
What? I'm not that mean.
You're like, yeah, 3 people who are like zooming out, so.
Okay. It says, show that the function y equals e to the 2x times the quantity a cosine 3x plus b cosine or sine 3x satisfies the differential equation y double prime minus 4y plus 13y equals 0. Okay. So, well, what I need to do is I'm going to be plugging in y prime, y double prime, and y into this equation and showing it'll simplify all the way down to 0. So the first thing I need to do is I need to calculate y prime, the derivative of y, and then using that I'm going to calculate y double prime, and then I'm going to plug those two answers into this formula and try to simplify everything down to get 0. Okay? Does that feel okay in like how to start as a plan? All right. So let's start with y prime. To do that, what's the first derivative that I need to do? A product rule. Excellent. So I'll have, like, this is my f, and that's like my g, right? So the derivative of f will require a chain rule because the exponent is 2x, right? Everybody's okay there? Isabel?
I'm just a little bit confused on why the
This is the chain rule that I did. So I have the derivative. I'm just taking the derivative of it. I'm just writing out steps, so I'm not trying to do it all at once, trying not to confuse everybody.
Break it up by like inside and outside.
I am trying to get you guys away from like notating everything as insides and outsides, especially when there's like 2 or 3 or 4 different opportunities to do a chain rule inside of the same problem, because I think it gets more overwhelming.
So you're just able to look right down. Yeah.
Well, the derivative of the e to the x is just e to the x. So the derivative of the outside, just same thing that I had.
Oh, it's within the product rule and then chain rule.
Wait, how come it's not e to the 2x?
Wait.
For like the chain rule part?
It is,
So the chain rule is in the product.
right? E to the 2x. Okay. Okay, are we ready to do the second part of the product now? Okay. So then I have f times the derivative of g. So to do that, I'm going to need to use a chain rule to do the derivative of a cosine 3x, because it's cosine of 3x, not cosine x. And I'll need a chain rule to do b times sine 3x, because it's sine 3x and not just sine x, right? Do the a and b's bother me? No, they're just coefficients, so I just kind of ignore them and just stick them on after I'm done with the derivative, right? Okay, when I do the derivative of cosine, I get negative sine. The inside stays the same. And then I have times the derivative of the inside.
What step is this? This is that second. B prime.
And then I do the derivative of sine, which is cosine. The inside stays the same. And then times the derivative of the inside.
So why you don't drop off?
So f prime, g, I'll answer that in a moment. I heard you. F, and then g prime. Okay. Why doesn't the a and b drop off? Well, if I take the derivative of like 2x squared, that's the same thing as 2 times the derivative of x squared, right? Same thing with a and b. Right? I just, same thing as if it was a number, right? I just ignore it, it stays in front.
Oh, I was thinking that you have like a 1 and like you drop it.
Yeah, it's,
Not like
if it was a plus sine yada yada yada, then the a just turns into a 0. But it's a times sine yada yada yada. So there it just sticks around, just like the 2 would stick around on a 2x. We do the derivative. Does that feel good?
yes.
Okay. All right. Yes, Rita.
For like the second chain rule you did,
Mhm.
what was the FX with GX? Oh wait, it's just cosine 3x cosine 3x.
So the outside function would be cosine x, and the inside function would be 3x. And then the other one, the outside function is sine x, and the inside is 3x. There's two separate chain rules, one for each of them.
Yeah,
Is that?
okay, that makes sense, sorry.
It's okay. Again, if you guys sounds like everybody had a rough time with it. I want to go through slowly. I'm taking big pauses in between for us to process. I'm not trying to steamroll through this. All right. So let's finish up doing these derivatives now. So the derivative of 2x is just 2. And the derivative of 3x is just 3. So I'm going to just move that 3 as a coefficient.
So why is simple? Oh, no. You take the negative.
The negative sign is there.
Yeah.
And the 3 comes from,
So then, what's in the, how is there still 3x in the sign?
because when we do the chain rule, the inside doesn't change, right? The inner function doesn't change, it just stays the same.
So why does
And then that.
Oh, I see.
Yeah.
Yeah, it's like the most.
Hold on, we're still doing it again?
No, I'm just like seeing if there's anything to cancel or like terms to combine here. Because all I'm doing is just kind of like distributing things out to see what I can group together in a clever way to make the next.
You could combine the A to 2x's.
We don't gotta go. They got
Yeah, you can. They'll just stay the same.
Well, I'm going to take that. Every term has an
Oh, no, it's sine. Yeah, I missed that part.
every term has an e to the 2x, so let's take those out. And then I'm going to group the cosine 3x's together, probably.
Can you say like 2 cosine?
Wait, so you grouped the
Oh,
cosines
okay.
together and then just pull out what was in the
Mm-hmm.
Yeah.
We might need that stuff first.
It starts off
Maybe.
on-
I don't know, it
I'm
depends.
like, oh yeah, that makes sense. But when I'm doing it, oh my god.
Could you leave it there?
And that's probably where I would leave it. Yeah, I wouldn't do anything more than that.
You couldn't just leave it at that first.
You could, but when I look at that, when I go to do, shh, if I went and left it at the step before, when I go to do my second derivative, I have 1, 2, 3, 4 product rules, and inside of each product rule is 2 chain rules. Because I'll have to do a chain rule for the e to the 2x part, and a chain rule for like the sine or cosine of 3x part, which doesn't sound like a lot of fun. So, yes. Yes. So, that's why I factored it this way, to reduce the amount of derivative rules I was going to have to do when I do y double prime. Because now the way I've written it, I have 1 product rule and 2 chain rules, which is a lot better than 4 product rules and 8 chain rules, right? So that's why I did that. Okay? I looked at this, and although this was going to be easy to combine like terms with, it was going to stink to do the derivative of. It's just going to be a lot. Does that feel okay?
So there'd be like one like this on the top.
So, no, probably not now, but we do differential equations
Yeah.
later in second semester, and for sure you'll do stuff like this then.
It's like a problem.
Yeah, we'll deal with
And
that.
it, but,
Second semester means
well, here's the thing, it won't feel this hard.
Yeah.
Like, this is something I would have been done with, like,
I like to do
minutes ago if I was just doing it on my own. And really, you guys would be done with by second semester on your own. Like, you might be still, like, monkeying around with the algebra if you didn't see, like, how to make the problem easier, but it's something you would be eminently doable. It feels overwhelming because this is the first time you're doing this.
Yeah.
It will get easier, okay? And it feels very hard right now.
Yeah.
But this will become like something that's not too bad eventually.
I like how you short.
Just not today. Right. And that's part of AP Calculus, is the people that find AP Calculus pretty easy and doable are good at seeing the shortcuts and going, oh, I can cut down, if I do this algebra thing, I can reduce the amount of derivatives I have to do immensely, and it can make the problem like tremendously easier, cut my work in half or by a quarter, or even like to make the problem trivial. To where it's just like, oh, look, this all simplified down to cosine, and then I just take the derivative of that. And I avoid having to do like chains and products and quotients and like all kinds of stuff because I did some algebra. Okay,
It's really just a bunch of that.
let's start. So again, this is going to be like my F, and this is going to be like my G for my product rule, right? So I'm going to have the derivative of F times G. Oops. Oh, no, that's fine. 2A. Elena, it's because the derivative of e to the x, the outside is just e to the x.
Yeah, so why do you have to do the derivative? No, like nothing's gonna happen.
He's just showing his work.
I'm just trying to really show my work in a painstaking fashion.
I gotcha.
And if you tried not to do anything, you would have missed the chain, right? The derivative of 2x.
Oh, the two. I missed the part because I thought we canceled out the two. That makes more sense.
First e to the because your base is e to the x, then your g is 2x. So he's just substituting that. Now you have to put it in. E to the x and you plug in your g, so it's just e to the x.
Okay. So now I'm going to do the derivative of g. Okay. So I'm going to ignore the 2a plus 3b because that's a coefficient. The derivative of cosine is
Sign that.
negative sine. And then the inside stays the same. And then I have times the derivative of the inside. So again, this is my F, and this is going to be my G prime.
Are you taking the prime of that one?
So we're doing the product right
I'm finishing the product rule because I haven't finished writing it out.
now. The G. Okay.
Yeah.
Pierce?
So how come you just
It's okay.
so for that second half there, where you had like that whole underlying G prime part,
Mhm.
you have 2a plus 3b. So like, how do you know that that's not?
Those are all constants. So it's just like a 7 out front.
Okay, so That's why, like, in that part, that's how, when you take the derivative of that thing, only the sign changes because that's the only thing you take.
Right. Because the other parts were constants that got pulled to the front. Exactly. Now I know it's a lousy trick to like put A's and B's in there.
Yeah.
I understand.
Leave them out in the front, and then you do that with cosine of that, which is negative sign. I'm trying to read this out loud. Oh, could you scroll over a little bit?
Yes, of course.
And then it'd be 2b minus 3a minus cosine 3x for the second. What's the next? Can you scroll to the derivative?
Mm-hmm.
Are you gonna give us a question like this on our test? Not this semester. I'm almost through this. I think we all know. Yes, like that one. Our grades. Yeah, extra credits fine. Let's do it. If he gives us extra credits, we're hundreds of dollars. Yeah, it's significantly harder. So he's like.
You guys don't need extra credit.
Wait,
You just want it.
I would think I need, there's a job like the left.
how did you have, like, on that last line, you have 2a plus 3b, but then when you go over, you change to 2b minus 3a?
There's different things to start with.
Oh, they were?
Yeah.
This is the,
I mean, if you look up here, it was always
Oh.
2b minus 3a.
So what happened in this stuff?
All I did was I just finished doing the derivatives,
Oh.
right? Like I did that, and I did that.
Oh.
Why is it 3 negative? Because the sign's negative?
Because the 9, yes, because the negative from the sign I pulled to the front also. Of course. So the negative comes from here and the 3 came from there. Right?
Oh, okay.
That's a fun problem. I don't really want to.
No, I got it.
Like, even though
Which
watching
one
you
is
do
what?
everything out and I have.
Braden?
questions, just like, it's a- Would this equation be like practical or is it just like, it's practical?
So differential equations has a ton of real world application. Like it's one of your core courses if you're going to do like most kinds of engineering. You'll have an entire course on differential equations and talk about like what are the applications. And even to a great extent, what you end up doing is you end up solving systems of differential equations.
So like this would be in a system of like 3 hours,
Yeah, sure.
and this could possibly be like the easiest one in the system.
Yeah, more than likely you'll be using like linear algebra techniques to deal with it. But like all kinds of real world stuff could be modeled by stuff like that. So, a noteworthy one. So your modern, like cocktail therapies for HIV drug treatments was developed first by modeling the problem with the system differential equations and solving, and then we developed the pharmaceuticals to actually like try that as the process. But like the initial idea was a mathematician. Like that's who won the was part of the Nobel Prize for that work, was the mathematician that built the model. But like differential equations are like huge application. Like anytime where something is changing, like in with time, is a differential equation is going to be a useful model. Now, this specific differential equation they gave us, I don't know. It could just be like something that like works out to be like a nice application of doing a bunch of chain rules. But the other thing is most real world applications aren't going to be single variate, like just have one variable in it. Most of them are going to have like going to be multivariate, which also makes life harder. Okay. So at this point, we're done with the calculus. Again, I'm going to guys, thank you. I'm going to clean this up now.
This isn't green?
Yeah, I was about to ask.
Just because I haven't finished with it, because I'm trying to talk to you about what I'm about to do, and then everybody's like wants to add their own little side comments into it. Actually, you know what? Let's just do it the simple way. Okay. Woof. All right. So let's take a look here. This is going to be my y double prime. And let's use the green, I guess. And this will be my, I'm going to use that version for my y single prime, where everything's all multiplied out. And then we need to do y double prime minus 4y prime plus 13y equals 0. I'm sorry, plus.
Separate like the Y's from each other.
Correct, because they're not even the same variable. Yes, they're y's, but one is like I think of this as like, you know, like this, and this. And now they don't even look like the same variable, right?
In the equation you put in like your y double prime, you combine it with stuff from 4y prime, right? Like, it's not separate.
Correct.
It's different.
Yeah.
That was because I just didn't know.
Yeah, correct. So the terms from y double prime and y prime can combine.
Okay.
Right? And they have to, right? So let's see here. Oh, you know what? Let's take a closer look at this pink, because I think we can do some better simplifying before we go plugging all that stuff in. So what I'm going to do is I'm going to multiply this whole thing out rather than have 2a plus 3b. So I'd have like 4a e to the 2x cosine 3x, and then 6b e to the 2x cosine 3x. And I think I like that, because then if I take this last one, if I distribute that out, I'm going to have 6b b e to the 2x cosine 3x, aha, and then minus 9a, e to the 2x cosine 3x. And look, we can combine some like terms there, right? So this guy and this guy. Well, because I just worried about the pieces with the cosines in them.
Oh.
I'm going to come back and do the sine pieces in a second. But it's just like there's only so much room on a line of paper. So I'm just going to pick the stuff that I can see could combine together. Yes. Right. Well, let me think for a moment. No, I'm just thinking if, like, what if we just... Here, this is a even better idea, okay? So that's a great question. I'm going to push the... if I push that coefficient in, now these are like terms that we can add together. So if I add these together, I have 12b and then minus 5a, which is the same thing we ended up here. Because if I look, everything else, right, all the parts of the variables are like termed now. So I can just add the coefficients like I would like 3x and 5x becomes 8x. Because we haven't dealt with the sign parts.
So which one is the right one? The second green or the second blue? Or are they both right? Just
They're the same.
So then which one should we use? And what's
Well,
better?
look, people keep asking me these sidetrack questions and we keep getting sidetracked, which is okay. I'm happy to do that, but that's why it feels like which one they're the same. I don't know which one we should use yet.
Oh, so we don't know.
I mean, it probably want to use the green one because it'll make combining like terms later probably easier, but I don't know. I'm doing this problem for the first time that I can remember.
Really?
I mean, I did it like when I picked the problems like a million years ago, but I don't do the problems like the day before I assign them to you guys. I do them way in advance. I'm like, oh, this looks like a fun problem. Let me do this. If I can't see what the answer is going to be right away or see like how involved it's going to be right away. Like this one I did, but I did like, you know.
Slightly sidetrack question.
Oh yeah, go ahead.
I think that you could have like look at the problem and you just know. Like this one when you just like oh, this is gonna be wide drive.
No, I can't do something like this in my head without writing it down because it's just too big.
Yeah.
But like I look at it, I'm like, okay, I know exactly what to do. And like the doing of it, hi.
Could we take Jacob and Prater real quick?
I mean, can you guys go for a minute?
Oh, yeah.
Okay. Like most of like 1 through 45, those are problems that I can kind of do in my head enough to where it's like I can see what to do right away and like, okay, I can see how bad this is going to get. This one's a little harder to see like how bad it's going to get or what's the clever way of trying to deal with this, Emma?
So when you were the green part, like
I'm sorry, you said something, your mouth was kind of covered and I missed what you just said.
sorry.
That's okay.
With the green part, like
Uh-huh.
4A, 2X, because I saw you multiply. Oh.
I did that, and then I did this, and then I did that. So 2 times 2 is 4, then I have the a, and then I times the e to the 2x in, and I times the cosine 3x in, right? That goes in, that goes in, that goes in. That goes in, that goes in, that goes in. Okay, so I just thought I answered that question, but ask it again because apparently I didn't understand.
Okay, so you have the 4a.
So to get the 4a e to the 2x from the line above, I distribute the 2 in. That gives me 4a. I distribute the e to the 2x in. That gives me 4a e to the 2x. I distribute the cosine 3x in. That gives me 4a e to the 2x times cosine 3x. And then I do the same thing to the 3b. That gives me this piece. And then I'm doing the same thing over here. You know, like, and that gives me this piece. I'm just doing the cosine pieces because those are the like term parts. Yes.
That's why I was.
Yeah, we addressed that.
Sorry.
That's okay.
I realized.
That's okay. Nope.
You just have to.
Right. So now we're going to do the sine part.
After this, are we have to do the same thing with y prime?
I don't think so, because I think it's already broken in the way that we're going to want it. All right, so if I do the same thing, we'll distribute this through and distribute that through. So we have 4 b e to the 2x sine 3x. And then we have minus 6a e to the 2x sine 3x. And we do the same thing here. So it's going to give me minus 6a e to the 2x sine 3x. And then it's going to give me minus 9b e to the 2x sine 3x. And so I combine that stuff together, and I'm going to have minus 12a e to the 2x sine 3x, and then minus 5b e to the 2x sine 3x. There's my expression for y prime, or double prime, that I'm going to use. So we're going to have y double prime come on, look, use your noodle here. You're using OneNote for a reason. Okay. Then we have minus 4y prime. So my y prime that I'm going to use is the green up there. So if I multiply minus 4 through on that, I have minus 8a e to the 2x cosine 3x. And then minus 8b e to the 2x sine 3x, and then plus 12a e to the 2x sine 3x, and then minus 12b e to the 2x cosine 3x. Everybody okay here?
Yes.
And then I have 13y. So when I do that, I'm going to have 13a e to the 2x cosine 3x and plus 13b, oops, e to the 2x sine 3x. And now we're just going to combine some like terms together. So I have minus 5 plus, minus 5a cosines. It's minus 8. That's 0 there, right? Yes, Tessa.
When you have the box, it's just the simple point cosines above it and then the simple point sines below it. Divides it times-
Yeah.
Okay.
Yeah. And then let's see. So then I have, let's see, b, I have minus 5b sine x, and then I have a minus 8b sine 3x, and then that 13, that cancels out and makes 0. And then I have minus 12 and plus 12. Those cancel out and make 0. And plus 12 and minus 12, those cancel out and become 0. So when I add this stuff all down, I get 0.
So all this work just for 0.
Because that's what the stuff added together is supposed to give us 0.
That was one problem. I know. You don't have to do this.
Oh my goodness, you guys are. I'm feeling like
This took the entire page. I'm gonna shut it off.
Hey, you know what? Maybe we overreached on this one. Okay? That's fine. I can admit that. Maybe that was too much too soon. That's fine.
But as you explained it, I picked up on all of
Hopefully that made caught a lot of misconceptions and straightened a lot of things out. This is part of the reason why I assigned the homework, some of the homeworks in the later stages that are not just like obvious problem, where it's like, oh, this was a mess, or like, oh, you really had to think about this in a clever way. It's just to get you to like learn something new, or to point out a misconception, or like, oh, there might be a better way to do this, or, you know, like what's, like, how do I sort through something that looks like this overwhelming? Now, this was messy when I did it, because again, it was the first time I'm doing this, and I didn't find like the cheapest route through it. But it worked. We did it. We got to the, I'm quite proud of myself for not making any kind of dumb arithmetic error, transcription error. Doing all of that and getting to the end and actually all adding up to give 0. I was pretty excited that I'm like, yes.
You did amazing.
Pierce.
I have another question.
Okay.
Could I ask you a homework problem?
I think we're ready for a new one, right?
Yes.
All right.
Okay.
A new homework problem or?
Yes, new homework problem.
Would you please do 41?
41?
I'm
Sure.
like good up until like the last like step or two, and then I'm trying to figure out what I was getting at.
Yeah. Okay. It's a tough one. There's a lot of chains in this. So what is this is all chain rules. The only thing going on is chain rules. What's the outer chain? What's the outermost function?
Sine squared x. Sine x. 2x.
X squared.
X squared.
'Cause the
Very
small
good.
out.
Wait, is this not a product rule too?
It is not.
Oh, I just watched like 7 hours of videos
Oh,
yesterday.
you saw
I was trying to remember all of it.
So this need not be done as a product rule. If you wanted to think about that as sine e to the sine squared t times sine e to the sine squared t, you could do it as a product rule. I would not recommend doing that. That feels like a lot of overkill to me. But you could. I would not. So when I do the derivative of the outside, that's just a power rule. So the squared becomes the coefficient. The inside stuff all stays the same. And the exponent gets 1 subtracted from it. I'm not going to write the 1. And then we have to do the derivative of the inside.
Sine squared.
Because sine squared, but why would we put that up to the outside?
Because that's what it means.
But isn't it squared at
So sine squared x means sine of x squared. That's what that symbol means.
I just don't get why it would x. That just doesn't make sense.
Because this is not the same thing as sine of
So it's exact-
x squared, right?
Because the sign is already for that.
Okay.
Don't do the exponent until after anyway.
Okay.
Is that okay?
I will be on Spanish and
Okay, so this piece comes down, and now we're going to do the derivative of this piece. What's the outermost function for this piece? Sine, right? So the derivative of sine is cosine. The inner stuff stays the same. And then we'll do-
Working your way in, basically.
Yeah, I'm just going to work from the outside in. And then I have to do that derivative.
Yes.
So again, that piece comes down, that piece comes down. To do the derivative of e to the sine squared t, that requires a chain rule. What is the outer function there? E to the x. The derivative of e is just, or e to the x is just e to the x. And then I have times the derivative of the insides. So that comes down, that comes down, that comes down. To do the derivative of sine squared t, that is a chain rule. The outer function is x squared, so the derivative of that is going to be 2 sine t, and we subtract 1 from the exponent, times the derivative of the inside, which is sine t. So that's what we have, right?
Oh,
So that we did the derivative of the outside, which is the power rule, times the derivative of the inside, which is the sine.
so that, you have the derivative of sine t and all that is squared, that's the same thing as the,
Sine squared t, yes.
so you just changed it to look like that. Of that.
Mm-hmm. Prater. Okay, so let's put this all together now. So this would be like my final answer. So I have that piece is there. That piece is there. That piece is there. That piece is there. And then this is my final piece. The chain rule.
That was a chain, okay.
Everything I've done is a chain rule.
If it was all a bunch of chains.
This was, what, 5 chains?
Okay.
4 chains. 1, 2, 3, 4 chains. Sorry. Which again, like, I think once you kind of understand what the chain rule is doing it this way, you're just doing like derivative outside times derivative inside, and just going one chain at a time is probably easier than writing down like f of x's and g of x's and h of x's and k of x's and q of x's and z of x, and like running through like an entire alphabet, right? It's just kind of looking at it going, okay, just take the derivative of the inside, just take the derivative of the inside, take the derivative of the inside, and just keep plowing away one link at a time. Isabel.
Do, 25.
25. Yes. Okay. So again, you look at this and you should see that this is a chain rule. Okay, what's the outer function? 5 to the x, right? So the derivative of 5 to the x is 5 to the x, but the inside of that just stays the same, times the natural log of 5. That's just the rule, right?
What is the rule?
So the derivative of a to the x is just a to the x times the natural log of a. So if this is e, what's the natural log of e? 1. So e to the x, derivative of e to x is just e to the x, which we knew already. Because the natural log of e is just 1. So that piece just drops off. Right? So it's just the same rule that we've seen. It just is a generalization.
So half.
So then I have times the derivative of the inside. What's going to be the easiest way to do the derivative of negative 1 over x? I definitely wouldn't do that.
I got no idea then.
I'm just going to write it as a power property or power rule. So I'm going to write it as x to negative x to the negative 1 because that is super easy. Could you do it as a quotient rule? Yes. Is it going to stink?
Yes.
Yeah. Do I want to waste my time doing that? No. So what do I have here? I have negative 1 times negative x to the negative 2, right? When I apply the power rule.
Yes.
So that just, I can write then as 5 e to the whatever over x squared. And I'm done. Isabel?
So, just like to the very, very beginning, why did you leave it as 5 to the negative x? That's just,
Because the derivative of a to the x is a to the x times the natural log. So that's what I have. The derivative of the outside, and then I have times the derivative of the inside. Okay? Lorenzo? Certainly. Isabel? Or I'm sorry, Elena?
79.
79? Sure. Emma, what's up?
just had a question about the, how did you get the
Okay, there was a little bit of noise going. You're talking kind of quiet, and I missed what you. Can you say it one more time for me?
how did you get
This. So I did the power rule. So when I did the derivative of this, the exponent becomes the coefficient, and I subtract 1 from the exponent. Right? Is that okay? Elena, which one? 70 something or another? 79. So it's going to be another like whole class problem.
No idea. I was doing them and I got, I just started looking at them. I was like,
Oh yeah,
wow.
yeah. That'll be fine. This is not.
I tried 75 and I did
75 was a monster. Turned out that was more than I thought it was going to be, probably by looking at it. All right. So it says the displacement of a particle on a vibrating string is given by the equation s of t equals yada, 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 where s is measured in centimeters and t in seconds. Find the velocity of the particle after t seconds. Well, I know velocity is just the first derivative of displacement, right? So all I need to do is take the derivative of 10 plus 1/4 sine of 10 pi t. So the derivative of 10 is 0, and I have 1/4. The derivative sine of 10 pi t requires a chain rule. The derivative of the outside is cosine, and the inside stay the same. And then derivative of the inside is going to be 10 pi. And I'm done. I just do some simplifying, I'll call that 5 pi over 2 cosine 10 pi t, but I'm done.
Was that simple?
Mm-hmm.
Honestly, I think 75
Yeah, anything after that was just, I looked at it and I just, we're going to spiral.
No, it's okay. 75 was, whenever you hear the word show in a problem,
Show or prove.
yeah, those typically end up being lengthy. Isabel. 45?
Wait, Mr. Tooley,
Yes.
so you got the 10 pi from taking the derivative of 10 pi t.
Yes.
Okay.
Correct. All right. So this is another like 4 chain rules problem. So when we look at this, what's the outside function? Cosine, right? So the derivative of the outside is negative sine. And then the inner stuff stays the same. And then we have the derivative of the inner stuff. And what is the outside function for? It's the square root, right? Which is the same as, we'll think about it as the 1/2. So that's going to be 1/2, and then the inside stuff stays the same. And then we have the derivative of the inner. Again, this stays the same, that stays the same. So the derivative of the, or what's the outer function for this sine of tan of pi x? Sine. So the derivative of the outside is cosine, and the inside stays the same. And we have the derivative of the inside. And again, another chain, right? The outer function is tangent. The derivative of that is secant squared. And the inside stays the same. Times the derivative of the inside. And now we're at the final step. So we have negative sine of square root sine tan of pi x. And then we have 1/2 sine of tan pi x to the negative 1/2. We have cosine pi, or of tan pi x. And then we have secant squared pi x, and then just the pi. Again, we had that part is there. That part is there. That part is there. That part is there. And then our last piece there. So again, we had 4 chains there. Yes, Pierce.
I don't know if there's like a possibility that would show up, but if the derivative of cosine is negative sine, is it possible to have like 5 derivative of cosine?
Sure.
But that should be positive sine.
Yep. So like if I wanted to do derivative of negative cosine, that's like negative the derivative of cosine, or negative 1. So that's negative 1 times negative sine. It's just sine.
Okay.
Yep, exactly right. Okay. All right. Elena.
You do
80?
or no, or is it 86 on the other?
I don't remember.
Was 80?
86?
Or is there not?
Yeah, there's parts A and B.
Yeah.
Air is being pumped into a spherical weather balloon. At any time t, the volume of the balloon is v of t, and its radius is r of t. What do the derivatives dv dr and dv dt represent? Okay, so both of these are rates. So the V is for volume, the rate of change of volume of the balloon with respect to the rate of change of radius of the balloon. So it's basically looking at how the volume is changing as the radius either grows or shrinks, right? Yeah, we have to do dv dt also. See if we can do this. What would we say here? Yeah, great. Right, because we're pumping air in at each second. We'd expect that volume to be growing, right? So this is basically, if we're talking about volume, and we're measuring things in centimeters, I think it said, right? No. Did it?
It doesn't say.
Oh, okay. Well, then let's not bother with it. Okay, part B, it says express dv dt in terms of dr dt. Okay. Oh. So if I take v of t, let's say, well, let's think about it this way. What's the volume formula for a sphere? 4/3 pi r cubed, right? So v of t would be 4/3 pi r of t cubed. So dv dt would be 4/3 pi 3 r of t squared dr dt. Where did the chain rule happen?
The R.
When I took the derivative r cubed of t, I did the derivative of the outside to get 3r of t squared times the derivative of r with respect to t. That's when the chain rule happened, right?
Yes.
But that's it for B.
Oh, that's nice.
Again, you could simplify some things, right? Like 3's cancel, yada, 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 but like, whatever. That was the hard part. Okay. Yeah. So next time, I assume you'll have some more questions from this homework, because I have a feeling some of us are going to go take a second pass through things because we got stuck on some stuff that we now feel probably better about doing. We'll finish up talking about chain rule because I still have this bonus section about inverses that I want to talk about. And we'll probably start implicit differentiation at the same time, which is nothing new. Okay, it's just going to be used, no new rules, just using the rules that we have in existence. So nothing new. Oh, I take that back. We do get some new rules in there, but they're for the inverse trig functions.
Okay.
So it's mostly not something that you'll see in the homework.
Okay.
But this problem that we just did, this is an excellent bridge into implicit differentiation.
Wait, so what is implicit differentiation?
We'll see tomorrow or next time on Friday. So we're a day behind on the schedule. Just keep that in mind.